So in the last lecture, we talked about how light is an electromagnetic wave, and I wanted to dive into that a little deeper to give meaning to these waves in a way that we can relate to in an everyday sort of way. If you've watched Sal's video, and I recommend you do, on waves with amplitude, frequency, and wavelength, you will recall that the velocity of a wave is equal to its wavelength times its frequency. And in our case, we know the speed of light is the speed of all the different electromagnetic waves that we're going to deal with. We denote that as c, and we just keep wavelength and frequency the same. Because c is fixed at 3 times 10 to the 8th meters per second, this means that wavelength is proportional to the inverse of f. In other words, this is how you would write frequency, and this is how you would write wavelength. And you can notice that they're inverses of each other. So if you speak of one frequency, you're also talking about the corresponding wavelength, and so on and so forth. The reason I bring that up is because we are about to talk about the entire electromagnetic spectrum. And the entire spectra is shown in both frequency on the left here, as well as wavelength on the right. We're going to start all the way at the bottom with the largest wavelengths, which correspondingly means the lowest frequencies, and work our way up. And I'm going to try to give you an everyday feel to what these things are. So we're going to start at the most useful frequency probably, which is electromagnetic waves that have a wavelength of 1 to 10 meters. So pretty big. These things are so big that they don't really interact with most objects that you and I deal with, because we generally don't muscle around or deal with objects that are 10 meters in size. Because of this, a 10 meter wavelength wave will generally only interact with a 10 meter object. Interact meaning that the wave bounces off, reflects, scatters, whatever. Anything smaller and the wave will pass right through. And that's useful if you want to transmit data from one place to another. And you do want that to happen when you're using a radio or a television. The electromagnetic waves, or light, that you're receiving are usually of these wavelengths because, specifically, they don't interfere with anything else on the way to your television. So there you go. Those are radio waves and TV waves. So wavelengths of an order of a meter, but you're probably more familiar with the frequency. For instance, if you dial into 91.3 FM, that would be 91.3 megahertz on this scale over here, corresponding to this frequency right here. But we're going to go ahead and continue with wavelength because it will give you a better idea size-wise on how things proceed. We are going to now move to the wavelengths that are on the order of everyday objects. In this case, 10 centimeters to 1 centimeter in wavelength. Because waves of this size will reflect off of like size objects and bigger, this is useful for the exact opposite of why television and radio is useful. In this case, you can send an electromagnetic wave at an object, and the wave will bounce back at you, and you can use that bouncing wave to determine where the object is. And that is what we call radar. This little word here is radar. Essentially, we have a transmitter or receiver on the ground, and we want to see an airplane in the sky, very quickly drawn airplane. This is a very, very good wavelength to send a beam of light, essentially, or electromagnetic wave, and have it bounce back so we can detect the airplane. And that is specifically why we call this range of the spectrum, or these wavelengths, radar. If you move to shorter wavelengths or higher frequencies, we move to a type of light that is able to excite and jostle around even smaller objects, like large molecules inside a material, for instance. If you excite it with enough of these waves, it will actually begin to heat up because it's vibrating so much. Now notice this light is not high enough frequency so that those small objects actually move around. They just sort of vibrate in place, but that still heats them up. We actually do that to cook our food, and we quite literally call the device a microwave because it is sending microwave light at our food to cook it. If you go beyond that, you move into an area where most things are transparent, called the infrared, and that it's infra means below, and it's called infra because it's below the red light wavelength. So this entire large range here is mostly transparent to most materials, but it's also noteworthy that our bodies actually emit light at around here, 20 microns wavelength. And that is noteworthy because if you put on goggles that are able to see at this wavelength, then most other materials are transparent, so you can see through walls, but you can see a person literally emitting light, like a light bulb, coming to your goggles, allowing you to see it. Otherwise, mostly transparent. Some materials start absorbing at shorter infrared wavelengths, but for the most part transparent. Then we get into a very special region called the visible area, or the visible spectrum. And the reason it's so special is because this is when most materials start absorbing and reflecting different parts of that spectrum of waves. And that's important because if you could detect that particular spectrum where most materials absorb and reflect, you could get a pretty good idea of what materials are made of, how strong they are, what texture they have, etc. And because we see at this special area, we generally have a good sense of how strong something is and what it's made of and what it will feel like, etc. That is basically visible light. It tells you the most about any type of material, and we're very lucky to be able to see at these wavelengths. So red light starts at around 780 nanometers, and we go all the way down to 380 nanometers, which is violet light, the highest frequency light. Violet. When you go beyond that to higher than violet, or ultraviolet, then you get to waves of wavelengths that are so small that most materials absorb all the light. This is why ultraviolet is so bad for your skin, because your skin absorbs all of that type of energy. So when the sun is emitting all this energy in the ultraviolet part of the spectrum, your skin is absorbing all of that. Notice all of the energy below that, your skin is pretty much letting it pass through because it's transparent to such long wavelengths. But all of this energy is absorbed, and that's why it's so important to take care of your skin, especially when you're outside with sunblock, etc. Now, notice we don't see an ultraviolet because since most things heavily absorb it, it would be very interesting to see it. It would just, everything would look black. X-rays are a very short wavelength, on the order of wavelength of an atom size. So we actually use X-rays to look all the way down to atomic scales. That's the most useful application. Beyond that, humans can't really reproducibly make waves of shorter wavelengths than this, but you have things called gamma rays and even cosmic rays up here that are 10 to the 19th, this is 10 to the 19th hertz, or cycles per second. An enormously high frequency, and once you get up into this range, only bodies out in space can produce something this energetic, and that's generally why we call these highest rays cosmic rays. So there you have it. This is the entire electromagnetic spectrum and all these different phenomena that you may have thought were completely separate from each other, such as cooking your food, seeing through goggles, watching your television and getting your skin burnt are all just part of light and the different parts of the electromagnetic spectrum and different wavelengths.